Hello everyone, I'm Keisuke Sugiura from University of Tsukuba. Today, we are going to present our work, PointODE, Lightweight Point Cloud Learning with Neural Ordinary Differential Equations on H. Point cloud is a basis for many real-world applications like 3D reconstruction, odometry, SLAM tracking, and so on. Deep learning has made a tremendous success on the point cloud analysis. And starting from PointNet, many deep learning architectures like PointConf, PointMLP, and PointGPT have been proposed. But the high accuracy of these models comes at the cost of increasing number of parameters and computational cost. For instance, PointBERT has 22 million parameters, and PointGPT uses 360 million parameters just to perform a simple classification task. So this poses a challenge to build a lightweight and efficient model to perform point cloud analysis on edge devices like FPGAs. So in this work, we propose PointODE, which is based on the recent model called PointMLP and neural ODEs, ordinary differential equations. Then we develop a lightweight version, which we call PointODE-elite. PointODE has advantages over the recent complicated networks. It is a simple architecture and based on MLP with residual connections like ResNets. It is also parameter efficient and uses less than 1 million parameters. It has low computational cost, less than 1 gigaflops. PointODE still achieves competitive accuracy to the state-of-the-art networks. And thanks to the simple architecture, we can easily implement PointODE on the FPGA to improve the inference speed and energy efficiency. PointNets are the first work and established the basis for deep learning-based point cloud analysis. PointNet is a very simple architecture consisting of the shared MLP and pooling operation. We first used the shared MLP to compute a high-dimensional feature for each point. Then we aggregate these per point features into a global feature. So the global feature encodes the information of the entire point cloud and can be used in subsequent tasks like classification and segmentation. PointNet++ is a sequel of PointNet and uses a hierarchical PointNet architecture like this. It repeats the sampling, grouping, and PointNet in order to gradually expand the receptive field and extract features at a varying scale. So PointNet++ can focus on both local and global features in a point cloud thanks to its hierarchical architecture. Later work has introduced increasingly more complex models, which employ carefully designed local feature extractors. PointMLP is proposed as a simple and MLP-based architecture without the use of complicated feature extractors. Similar to PointNet++, PointMLP performs the hierarchical feature learning. The network has an embedding layer, which is followed by 4 stages. So the later stages compute higher dimensional features for fewer represented points. And each stage contains residual point blocks, which are similar to those in ResNets. And there is a strong connection between ResNets and ODEs. A sequence of residual blocks in ResNet can be seen as a discrete version of the corresponding ODE. Based on this observation, neural ODEs replace a sequence of res blocks with a single ODE-based block. And this ODE block is also a residual network with an arbitrary ODE solver. So in other words, we can utilize neural ODEs to compress ResNet-like architectures. The forward pass of C-separate res blocks is now replaced by COD solver iterations of the same OD-based block, which is C times more parameter efficient. PointMLP has a sequence of residual point blocks in each stage. This means we can apply neural ODEs to replace these residual blocks with a single OD block. This OD-based block has a similar architecture to the original residual block, with minor differences. We consider two variants of PointODE, regular and elite. In the regular variant, we first reorder the layers in each stage of PointMLP, like this. Then we apply neural ODEs to convert a sequence of 4 residual point blocks into a single OD-based block. Compared to the original PointMLP, this regular version has 2.7 times less parameters and 2.6 times less computational cost. And PointODE-elite is a lightweight version of PointODE regular. We reduce the number of feature dimensions in each stage and employ a bottleneck architecture in each OD-based block. Compared to the regular version, this elite version has 8.5 times less parameters, and compared to the original PointMLP, this elite version has 23 times less parameters and 25 times less computational cost. We use the Lynx SoC as a target device. The feature extraction part of the PointODE model is implemented as a single IP core. This IP core and XI components are placed on the programmable logic part. The host CPU handles the other parts like the classification layer, sampling, and grouping. All parameters and other necessary data are stored on chip to reduce the data transfer overhead. We use a Xilinx ZC104 evaluation kit as a target device, and we use Vitis HLS to develop a custom IP core. We evaluate the accuracy of PointODE on two famous point cloud classification datasets, ModernNet 40 and ScanObject NN. First, we show the accuracy on two classification datasets. As we can see, a PointODE-elite keeps accuracy within 1% of PointMLP with 23 times less parameters, and FPGA implementation achieves similar accuracy to that of the software counterpart. PointODE is a simple MLP-based architecture, and it outperforms more sophisticated networks with carefully designed feature extractors like KPConf, DGCNN, and PT, which are based on the custom convolution kernel, graph convolution, and transformers. This result highlights the potential of simple MLP-based approach for point cloud analysis. And our FPGA implementation only consumes 450 milliwatts of power, and it is 3.5 times more energy efficient than ARM Cortex CPU. In addition, our implementation is 16 times and 8 times more energy efficient than NVIDIA Jetson Nano and Xavier NX. Thanks to the low number of parameters, we can store parameters and other necessary data on VRAM and URAM resources. We could employ neural network quantization techniques to further save on-chip memory. We have a demonstration video of the proposed PointODE-elite, which is also available on YouTube. And the classification task is running on the CPU, and the inference time is around 300 milliseconds. And now the classification task is running on the FPGA part, and the inference time is reduced from 300 milliseconds to around 70 milliseconds, leading to a 4 times speedup. We summarize this presentation. We presented PointODE, a simple MLP-based residual network for point cloud processing. PointODE uses neural ODEs to compress the PointMLP network by fusing a sequence of res blocks into a single ODE-based block. PointODE is a parameter-efficient model with low computational cost. It shows competitive accuracy on the famous classification datasets, and FPGA implementation effectively improves the inference speed and energy efficiency. There are many possibilities for future work. We need to evaluate on larger scale datasets or different tasks other than classification. We also need to do more theoretical analysis of neural ODEs and more ablation studies on the choice of hyperparameters. So thank you for your listening.